This is the maths from 2020. I'll be doing the long questions 2, 3, 4, and 5 in this video. I'll quickly say as a disclaimer, I probably won't get full marks in this because I've been a bit lazy sometimes and just not quite finished off arguments just because I'm not as good at long questions as I am with the short ones. But anyway, let's get into it. So if you do spot any mistakes, feel free to clarify them in the comments and fix my work for me. Just because, yeah. Question number 2 then. So we've got these two functions here, and this is a really interesting question because you can do the entire question in two different ways, which I just think is quite interesting. You've got two functions, and you have to start with the number 1 and then just apply the functions in a bunch of ways, in a bunch of different orders, and it's asking about which numbers you can actually make when you do that. But then, rather than doing any of that, it starts talking about the binary expansion of 100. Now, I'm quite good at binary, so it doesn't take me too long to write these out. But if you're not very used to binary, what it does is it just writes everything in powers of 2, and then writes it as a decimal, as a series of zeros and ones with these things. So, okay, you have one lot of 2 to the 6, one lot of 2 to the 5, no 2 to the 4s, no 2 to the 3s, a 2 to the 2, no 2 to the 1s, and no 2 to the 0s. So this is binary form. You put in the 0s for when you don't have a power of 2, and you start at 2 to the 0, and you just go up in 2 to the 0, 2 to the 1, 2 to the 2, which I have, 2 to the 3, 2 to the 4, 2 to the 5, which I have, and 2 to the 6, which I have, and then you stop at the biggest one. Okay, so why is it asking me to do that, is the question. Show that 100 is an S by describing a combination of F's and G's that do it. Now, the thing is, you've just been asked to write 100 in this form, but now it's asking about the functions thing. So why did it ask you to do that? So what I decided to do was I decided to write 36 in binary form. You can double check my work if you want to. And then I wrote 67 in it, and you can double check my work there as well if you want to. And I was like, what on earth is going on here? Like, can I see a pattern in this binary form from these things here? And I couldn't really see it. What I did think was interesting was that the zeros always come in pairs. I think that's interesting about these numbers, so maybe that will be relevant later. But for now I just thought, okay, let's just do this without binary. I'm not smart enough to immediately realize how this is helpful, so let's do this without binary. Now if you've ended up at 100, notice these two functions. This one, because n is an integer, and this is all just doing stuff with integers, when you put an integer into here, you're going to get an odd number, and 100 isn't odd. So actually 100 the last function you must have applied was g, and you must have done that to 25. Right. Now, because 25 times 4 is 100. But 25 is odd, so it can't have been timesing something by 4. It must have been this. And of course you can do 12 times 2 is 24 plus 1 to make 25. And so you must have applied f before this, and you must have applied that to 12. But again, 12 is even, so you must have therefore applied g to 3. 3 is odd, so you then must have applied f. And f to 1 will get that done. So let's just double check this. F of 1 times by 2 is, and then plus 1 is 3. Then apply g to 3, which is 12. Then apply f to 12, which is 25. Then apply g to 25, and you get 100. So this definitely works just by going backwards. Good. Show that 200 is not an S. Now there's a couple of ways to do this. The much easier way is to think about this not in binary, but I was determined to do this in binary because I didn't just want to ignore this. In binary, 200 is this, and this really piqued my interest because that thing that I noticed straight away of these zeros appearing in even number of batches doesn't happen in 200. So I was like, that's got to be it. I have to be right. That has to be why this 200 doesn't work. So then I thought about what happens in binary to a number, to f and g. So now I'm going to do this in binary, not in real base 10. I'm going to do this in binary. What does g do to this? Well, g times this by 4. But again, notice how binary works. This is the number of 2 to the 0s, this is the number of 2 to the 1s, this is the number of 2 to the 2s. But 2 to the 2 is 4. So when you apply g, when you times this by 4, you just get 100. Right? Because this is 2 to the 2, and you've got one lot of 4, which is 2 to the 2, so that's 4, so that's good. And now when you apply f, you times by 2, which shifts the digits along by 1, because this is 2, this digit is 2 times greater than this digit. So you shift along by 1, and then add 1, which just puts a 1 here. So you shift this along by 1 to get 1, 0, and then add 1 to get 1, 1. And you can do that again if you want to. If you times that by 4, you just end up adding 2 more zeros, because this number is 4 times 4 is 16, but 16 is just 1, 0, 0, 0, so you just add 2 zeros to that. And this one, if you times it by 2, again, you shift the digits along to get 1, 0, 0, 0, add 1 to it to get 1, 0, 0, 1. And you notice this pattern when you do this, which is that g just adds 2 zeros onto the end of a number, and f just slams a 1 on the end of the number, essentially. because the digits shift 1 to the left, and then you put a 1 there, and essentially it's just slamming a 1 on the end of it. So that's quite cool. And then you look back at this number and you think, well, okay, well, how did that happen? How did you get 1 0 here? And the thing is, you can't. You can't get 1 0 here, because the only thing you can do is either add 2 zeros at a time or put a 1 on the end. You can't end up with 1 0. The other way to think about it is look at this end bit. There are 3 zeros. You can't have 3 zeros at the end of any of these numbers, because you can either have 2 zeros or 4 zeros or a 1 or 2 1s or whatever. You can't have 3 zeros. So this definitely isn't it. The much easier way of thinking about this is in regular numbers, though. So I was really proud of myself for figuring out all of that. And then I realized, actually, if you just stuck to regular numbers, you can think, well, 200 is even, so you must have applied G last. And you must have applied it to 50. But the thing is, you can't make 50, but 50 is even, so it couldn't have been this function that got you 50. But it couldn't have been this one either, because 12.5 times 4 is it 12? Yeah, it's times 4 is 50, and you can't use 12.5, so nothing makes 50. So that was a much easier way of explaining why 200 wasn't in it, but I was proud of myself for using binary. Anyway, the functions f and g, yeah, sure, show that if n is an s, there is only one combination that would do that. Again, there's a couple of ways of thinking about this. There's one way of thinking about it in binary, and there's one that's not. What you can say is, if n is odd, if the number you're looking at is odd, you must have applied f as the last thing that you did. And like if that thing is still odd, you must have used f before that. And if that thing is even, you must have used g, or a multiple of 4 more accurately. But in either case, if you work backwards, you realize there's only one chain that's possible, because this function only gives you odds, and this one only gives you evens. So if you think about this as a function machine, but instead of going forwards, just go backwards, you only have one choice for what function you use, depending on whether this is odd or even. Right? So there's no choice anywhere here. You must just, if you work backwards, end up with a single sequence that you have, which then you apply the other way around and you get the single sequence forwards. Again, you can think of this in binary, because again, when you think of binary as being g just adding 2 zeros, that is exceptional use of the word 2. This should be 2TWO, of course, but whatever. When you add 2 zeros onto the end, or just slam a 1 onto the end, you can think of the binary representation of literally just reading what you're doing. So you start with 1, you slam a 1 on the end, so this number must have had applied f first, then you applied g to add these 2 zeros, then you applied f to put this 1 on the end, then you applied g, right? Which we can see exactly is what we did. F, then g, then f, then g, right? F, then g, then f, then g. And because every number has a unique binary representation, of course, that means there's a unique string of f and g's that will make it. Good. Part 5, I believe this is, if I can read Roman numerals correctly. Let UK be the number of elements in S that lie in this range. So this is the number of numbers that you can make through these things, starting at 1, in between these two things, is what this is saying. So this is a bit confusing. I'm going to do this in binary, because I think this is easier to do in binary. Now, these numbers are in binary. So this is the number 1, this is the number you think of as 2. Now, in between 1 and 2, there's only one number that you can make in between these two things, and that's 1. In between 2 and 4, there's only, you can make 3, because you can just slam a 1 on the end of this number, of course, and that's it. And the reason this is good to do in binary is because these are just the 1-digit numbers, these are the 2-digit numbers in binary, these are the 3-digit numbers, and so on. So what 3-digit numbers can I make? Well, I can put a 1 on the end of that, or I can put 2 zeros on the end of that. And maybe you can see where I'm going with this. So the 4-digit numbers now, I can either put a 1 on the end of this, a 1 on the end of that, or 2 zeros on the end of this. So I make 3. And this is where this pattern is coming from, right? Because I'm doing this in binary and I'm saying, here are all the things with 4 digits. To get a 4-digit number, you either add 2 digits to the 2-digit number ones, or add 1 digit, the 1, to the end of the 3-digit ones. And so all the number of numbers in each of these ranges, which is this range in binary, in case I didn't make this clear, the reason I've done these ranges is because that's what this is in binary. This is 2 to the 2, sorry, this is 2 to the 1 to 2 to the 3, this is 2 to the 3 to 2 to the 4, and so on. The number of numbers in there are just this row add 2 zeros, and this row with a 1 on the end. So whatever numbers I can make in here, I can make all of them in here by just adding 2 zeros to these ones, or 1 to all of these. So of course this must hold, therefore. Good. and I guess I could make an extra note here that there will be no extra numbers in here that don't come about from doing that process here, because of course I can do these things backwards as well. So there are no magic numbers appearing in any of these lists that don't appear beforehand, because I could just apply these rules backwards and make numbers in the rows beforehand. So there's no dodgy stuff going on there. Last bit, so denote S of k to be the numbers in S, that are in this range. Now notice the difference here. Instead of just doing like one of these ranges, S of k is adding up everything from the very start. Right? So S of k is adding up all the ranges together. So S of k is this. Right? It's adding up all of the previous rows, right? Because it's starting all the way back from 1 and so on. Now what I'm going to do is I'm going to take this rule here and just write it out a few times. And it took me a while to come up with this method, but I'm just going to write out u2 is u1 plus u0, just following this rule, and then so on and so on, and I'm going to keep going until I get all the way to here. And now what I can do is, if I look at this left-hand side, that's almost exactly S of k plus 2, because S of k plus 2 is just all of the u's below it, but we go all the way back down to u0, and I'm missing those. So let's just add in u0 and u1 to this side, and now this whole thing is S of k plus 2. This whole side. But of course I can't just do that, so I'm going to add in u0 and u1 here. But that works really well too, because now look at these numbers just here. That's precisely sk plus 1, because I've got all the numbers u to 0 to uk plus 1. So we've got s of k plus 2 here, s of k plus 1 here. Now s of k is all of this precisely. I don't need this, so that's just going to still be left here. But u1, I think we decided earlier, was equal to 1, and I can just guess that it is, because that makes that work, and I'll have my answer. So that is finally the first question done, and we're on to the second question, which is, I believe, about an elliptic function, which is cool. It's functions of the form y squared equals f of x. So that's quite cool. What are the values of a and b? Well, they're on the x-axis, so they happen when y is 0, so we just shove y as 0 into this. We can factorize a couple of times, and we get minus 1. 0 is the other root, of course, and 1. So minus 1 and 1. Good. By completing the square, find the value of delta. So completing the square only really works on square things. So I'm going to complete the square on this side, and I get this. And then I'm going to sit here and wonder how that helps. And it took me a little while to figure it out, but eventually I realized, okay, look at this thing here. If you put in some value like 3/4, 3/4 minus a half is a quarter, squared is a 16th or whatever. And 3/4 is like a quarter away from this. Now, if you go a quarter the other direction and put in a quarter, which is a quarter away from a half in the other direction, a quarter minus a half is minus a quarter, squared is still a 16th. So there's some symmetry going on here when you put in values of y that are either side of a half, right? And we meant, I think, did I mention this earlier in the video? When you square things, of course, with a difference in between them, like 5 minus 3 squared is the same as 3 minus 5 squared. Like, the negative squared is the same thing as the positives do. So when you put in things either side of a half in here, you're going to get the same number. So there's some symmetry here around the line y equals a half. But of course you look at the graph and you realize, okay, well the graph clearly has symmetry here, so that implies that delta is a half, and therefore y is a half. And then I realized that apparently I did that completely wrong, because I've just done that in order to deduce that delta is a half. So there must be some other way of deducing that delta is a half here that I missed. But I know, it's more efficient, isn't it, to do 2 parts in one, so cool. Find a cubic equation that has roots alpha, beta, gamma. Now, okay, well, if I just substitute in y as a half, then that's when I get x solutions of alpha, beta, and gamma, right? So I just need to substitute y as a half into this. But of course, putting a half into this gets me 0, and I just get this. So that cubic has roots. I was a bit confused how to answer this. Maybe this is the answer, because this has, I would say that this has solutions at x equals a half. At x equals alpha, beta, and gamma. I would say this has roots at alpha, beta, gamma, just because roots imply that you're actually looking at a proper function. So I don't really know what the answer to this is, but it's one of these two things. But again, yeah, all you need to do is put in y as a half into this elliptic curve, and you'll end up looking for x values that correspond to them, which is alpha, beta, and gamma. So put in y as a half into here, and you get this. Okay, good. Next bit. By considering the factorization of the cubic. So this is the cubic here. Find the value of alpha plus e. Okay. Now, if this thing factorizes and has roots alpha, beta, gamma, then it must factorize to this. And if you do further maths, you'll be very comfortable with what I'm about to do. But essentially, if you imagine expanding this out, you can then compare coefficients. So for example, the only thing on this side that doesn't have an x in it is when you do alpha plus times beta times gamma with a bunch of negatives, I guess, to make this, and that must be the same as a quarter. And the only way to make x squared term, it doesn't matter which one you want to do, but the only way to make x squared x terms is to do x times beta times gamma, which will give you this, or alpha times x times gamma, which will give you this, or what was the last one? The alpha beta one, alpha times beta times x. Right. So when you expand this out, you get these three terms in x, which must correspond to this minus 1, and the two negatives make all these positive. And then finally, to get x squareds, you either do x times minus gamma, or x times minus beta times x, or alpha minus alpha times x, and you get this. And that equals 0 because there are 0 x squared terms. I could have expanded that out properly and actually done that, but because I do a lot of further maths, I'm just very comfortable writing that down. Okay, but of course you can times that by minus 1 and you get the solution to what they're asking you. Good. Let's C denote the circle which has points alpha delta and beta delta as ends of diameter. Remember, delta is a half. I decided that earlier. So we have a circle here. It's got a center in between these 2 points. So clearly the y-coordinate is delta, and the x-coordinate is the average of these two things. So that would be alpha plus beta over 2. Okay, and so the radius of the circle is going to be the difference between this value and this value, I believe. Sorry, not this value, because that's this one over here. It's going to be the difference between this value and this value. You could have also done this one and this one, but it's not going to make a difference. So that's the radius. So the equation of the circle is x minus this squared plus y minus this squared equals this squared. Okay. Show that C intersects S at 2 other points, these being these 2 points, which look like they have the same x-coordinate roughly, which is what this is saying. Now, this is a horrific equation to solve. You need to look back in your notes for a start. On the previous slide, I wrote down something that looked very much like this. I'll just show it again really quickly. It was this here. So this here equals that. So first thing I'll do is replace that with that. So I can replace this with that, because I wrote it down earlier. And now again, this looks like a horrific equation. Do not try and solve this. They've done this for a reason. They like doing this. They're trying to lead you into a way to solve this, right? What you need to say is this is a cubic equation that has a single x cubed. It has a single x squared, because when you expand that out, you're just going to get x squared plus some amount of x's plus whatever this is squared. And there's no other x squareds here. And then this is just an x, which will combine with some x's from here, but that doesn't matter, or it's not going to matter. This is a constant, this is a constant. So it wants you to do the same thing as it did before. Right? It wants you to say that the sum of the 3 roots of this is just equal to the x squared coefficient, which in this case was 0, and then I times by minus 1, it was still 0. But the sum of this roots here is still going to be equal to the x squared coefficient, based on this kind of idea of expanding this out and comparing. And the x squared coefficient here is 1. So the sum of these roots, whatever the roots are to this, is going to be minus 1, because you times it by minus 1 and you get minus 1. But alpha and beta I know are roots. If I just call the other root epsilon, I'll get the sum of the roots is minus 1 here. But I already know that alpha plus beta, based on this solution here, alpha plus beta is minus gamma. So I'll just replace those with a minus gamma, and I'll get epsilon equals gamma minus 1. That's in terms of gamma there. A very difficult question to finish that off. But again, you need to use these things that you've learned in the previous parts of the question. That's what they're there for. They're trying to help you out with these questions. If you do a lot of step 1 questions, that would really help, because they do a lot of this kind of idea as well. And likewise, if you're prepping for the the step exams later on in the year, these would be good warm-up questions, I think. Okay, so anyway, we've got another question here. I've got a couple more questions to go. We're looking at, so this is, I said at the start of the video, I'm not going to get full marks on this paper. This bit is why. Even functions look like this. I've talked about these in previous videos, where any x input that you put in is the same as any negative x input you put in, because the graph is symmetrical about the y-axis, which is this answer to the first bit. Odd functions don't do that. Odd functions look a bit like this, whereby any x input you put in gives you some f of x that's equal to the negative of the f of x you put if you put in the negative f of x. Which sounds a bit complicated, but let me explain that again. If you put in 1 here, say, you get some input of like, some output of like 3. So if you put in minus 1, you get an output of minus 3. That's what I'm saying there. What symmetry does this have? Well, actually, what it means is if you rotate this graph, this is another one that's easier to see. If you rotate this graph around the origin, you have rotational symmetry order 2, and that's probably just something that's worth memorizing. But what this means is if you rotate it around, after 180 degrees it looks the same, and then after another 180 degrees it looks the same again. So it's rotational symmetry order 2 about the origin. Use the symmetries to show that the derivatives of an even is an odd, now, and the derivative of an odd is an even. Now, the derivative of this function is just what the tangents look like. So, for example, the tangent here, it looks like this, and the tangent here looks like this, and on the other side, the tangents look like this and this. And so the derivative is whatever the gradients of the tangents are. But you can see when you flip the tangents, or reflect the tangents in the y-axis, they go to their negative counterpart gradients. And so, well, that's the definition of an odd, right? When you have some positive number that when it flips over becomes the negative, right? So this 3, when it flipped over, became a minus 3. So this derivative is going to flip to an even, to a odd function because these signs are changing when you flip them in the y-axis. But likewise here, when you find the gradients, and 0 of course flips to 0, which is why it's the same, the gradient here is the same as the gradient here, so roughly at 0.7 or whatever. The gradient here is the same as here, and likewise the gradient here is the same as here, and so on. And that's because when you rotate this graph around, because it has order symmetry 2, when you rotate this point around, this line is going to be in the same direction as it was originally, and then again when it goes around again. And this is essentially what they've written. I've just drawn it as pictures and said it out loud, so I think I would get the marks for that. I maybe would have to clean it up by actually writing down some of these things that they've written here, but I mean, that's what they wrote. It's basically what I said. So anyway, next part. And this is basically pointless. You can do this entire next part without it, I think, so I'm a bit confused about some of that. Anyway, now we've got this picture, this question here. We've got theta. They've defined this interestingly. Theta is defined to be from here going outwards. So this angle looks like it's, well, maybe it's not that interesting. Theta is 0 would be along this line, and then theta is bigger goes up here, and then you can make theta negative by putting it down here instead. So if you draw a line there, this is negative theta, is what they're saying. If you go downwards, you have this negative angle, which you usually don't get, but whatever. Now, A of theta is this area here. A of minus theta is this area down here, underneath this line. And it's saying, show that A of alpha plus A of minus, A of theta plus A of minus theta is a half. Now I'm going to do a couple of things here, and it's supposed to be geometrically. Firstly, I'm going to show that these two triangles are congruent. They have the same angle here, because this is of course just theta. They have the same angle, they have the same length here, they share a length here. So same angle here, they share a length here. And the other thing I think I can argue is that, what else can I argue? How did I do this? I don't remember. This length, I believe, is the same as this length. How did I show that? Oh, of course, you can do some trig stuff here, can't you? This length, if you did some cos, this length you would find as, because this is 90 degrees, of course, right? Yeah, this is 90 degrees. Sorry, that's what I was thinking. This is 90 degrees because this has gradient 1 and this has gradient -1, so they're reciprocals of each other. So this is 90 degrees. So by RSH, these two triangles are congruent. That's what I was thinking here. All the angles are the same, and then this length is shared, so they're congruent. So these two triangles are congruent. So these two lengths are congruent, and these two lengths are congruent because they're both side length 1. And finally, because this angle is 90 and so is this angle is the same as this angle, which means this angle is the same as this one down here. So these two triangles are also congruent because side angle, and then this angle is the same as this angle. They're both 45 degrees. I've got more than enough, I think, to show that these two sides triangles are congruent. So this is A minus theta. But of course, that means that A of theta plus A minus theta is just this angle here. Sorry, this area here, which is 1 times 1 times a half, which is a half. So I think I'm done there. Now, next bit, determine a formula for A theta. It's very vague as to what formula it wants. I don't know whether all methods would lead to the same formula. This is the point a half because it's on the line y equals x. So I can say a couple of things here. Firstly, this length is a half squared plus a half squared square rooted, which is 1 over root 2. I can also say that this area is a quarter because it's 1 times a half because it's a triangle. So that area there is a quarter. So this total area is just a quarter plus this area here, which is why I found this length, because now I can describe this one. If I just call this little bit L, I can say L, or I can say, was it tan theta? Yeah, tan theta is L over this. I can rearrange for L, and then the area of this triangle up here is a half times this times L, which is that. Just rearrange, or just sort that out, and you get this formula for the area in terms of theta. And then it asks you to sketch the graph between minus 45 and 45. Now you should know what the tan graph looks like. It looks, between minus 45 and 45, it looks a bit like this. And all the graph that we're going to sketch is that graph squashed down a bit by factor 4 and then moved up a quarter. So it should look a bit like that, very roughly speaking, with this being a quarter. In light of the identity of 2 part A, which is this identity here, what symmetry does this graph have? Well, I think I can see that this looks a bit like an odd function that I was drawing earlier, except it's not based around the origin, it's based here. So I think this, I can just say, based on the fact that it looks like an odd function before, it's a rotational symmetry order 2 around this point a quarter here. So if I were to turn it around this point a quarter, just pretend the axes weren't there, I'd have that. And that is the answer. I'm not 100% sure how I'm supposed to use this, but I don't think it actually needs me to say that. I think I can say it's just an odd function with shifted up a bit, so I can just say it's rotational about there. Without explicitly differentiating, explain why that's 0. Well, this is an inflection point, and inflection points are defined by the second derivative being 0. So I think that's all I have to say there as well. Good, last bit. These people are playing a game because they're really bored. Miriam's allowed to eat as many sweets as there have been sunny days up to that point. Adam is only allowed to eat on rainy days. She can only eat on, and she can eat on any day. Adam is only allowed to eat on rainy days, and he gets to eat K sweets on any rainy day. So this is a really nice example of how this works. So the first day is rainy, so Miriam can't eat, but then she eats 1 because there's been 1 sunny day, then 2 because there's been 2. Even though this day is rainy, she's still allowed to eat 2 because there have been 2 sunny days, and then likewise 2, and then 3 because this is the 3rd sunny day, then 4, and then 4 again because there have been 4 sunny before that. Whereas Adam only is allowed to, he can't eat on sunny days. He's only allowed to eat sweets on rainy days, and he's allowed to eat the number of days that day is. So there. Okay, cool. And it just happens that these two amounts are the same here, which is interesting. If the holiday is 30 days, 15 sunny, 15 rainy, what arrangements would lead Miriam to eat the greatest number? Now, remember, she can eat for as many sunny days as there have been. So if we front load all of the sunny days and have 15 sunny days first, then 15 rainy, she can eat 1 on the first day, 2 on the second day, because there have been 2 sunny days, 3 on the third, 4 on the fifth, and so on. And then on the 16th day, even though it's raining, she's still allowed to eat on rainy days, and she can eat the number of sunny days there have been. So she's allowed to still eat 15 sweets on that 16th day, and then 15 after that, 15 after that, and so on. So she can eat this many up to here, and then just 15 after that every day, which is 15 lots of 15. Work that out, and you get this. This is the triangular formula. 15 times 16 over 2 will give you this sum, and then 15 times 15 is this, and work that out and you get this. Likewise, the least number of sweets she's going to be allowed to eat is when all the rain comes first, because she can't eat sweets unless there's been a sunny day. So if you just do 15 rainy days in a row, she can't eat anything for the first 15 days, and then the first sunny day on the 16th, she eats 1 sweet, then 2, then 3, then 4, and so on, and you just do 15 times 16 over 2, which is this here. Okay, what about yeah, sure. Show Adam eats the same number in these cases. So if there are 15 sun, then 15 rain, show Adam also eats this many. Now again, let's just check this. He only eats sweets on rainy days and can eat that number. So here, the 16th day is rainy. He can't eat anything for the first 15. The 16th day is rainy, so he can eat 16. Then the 17th day is, so he can eat 17, and the 18th, and so on, all the way up to the 30th, where he can eat 30. This is a triangular formula. You can do 30 times 31 over 2, and then take away the 1 to 15 that you're missing. So you do this formula to find 1 to 30, and then take away 1 to 15, which is this. Work that out, and you get this. You probably could have just had belief in yourself that you'd done the logic correctly, and not bothered to work this out, and just written it down as if it was the same thing. They're not going to check that, are they? And then in the other case, 15 rain, so he's allowed to eat 1 on the first day, 2 on the second day, 3 on the third day. Very straightforward, and then none on the sunny days afterwards. This is just 15 times 16 over 2, which is the maths we did the first time, and we get this. Good. Suppose in a sequence of sunny and rainy days, we swap a rainy day for the sunny day. So we swap a rainy day with a sunny day that follows it. So instead of this, we're going to do sun, rain. Now, if we swap this for sun, rain, Miriam can eat one on the first sunny day, and then she can also eat one on the second rainy day, because there's been one sunny day. So she's going to increase her amount by 1. And then everything else that follows will be identical. So she increases by 1. But likewise, Adam, if we swap this for this, he's not allowed to eat on the sunny day, if we swap this for a sun, this for a rain, but he can eat 2 on the rainy day because it's now day 2. So he'll also increase by 1, and everything else will stay the same. So both of them will increase by 1. If the holiday has 15 sunny and 15 rainy days, must Adam and Miriam eat the same number of sweets? So they eat the same number of sweets in this case, and this case. And if we change a sunny day for a rainy day, in that order, nothing happened. It would both increase by 1. What about if we change in the other order? What if we change a sunny day for a rainy day that comes afterwards? Well, if you do that, just quickly do it in your head. Change this sun for rain, so do rain then sun. She's only going to eat 1 on this day, and then she can eat 2 on this day. So her total amount goes down by 1. And if you change this for a rain, this for a sun, Adam can eat 3 on this day because it's the 3rd day and it's raining, but he can't eat any on this. So again, he goes down by 1 from 4 to 3. It'll go 3, 0 instead of 0, 4. So if you swap a rain for a sun in this order, both go up by 1. If you swap rain and sun in the other order, they both go down by 1. And you have a case, or you have multiple cases actually, where they eat the same number of sweets. So what we can say is we have this base case where they eat the same number, and any change we make to the sun and rain, as long as we don't change the total number of sun and rain days, as long as we just do swaps, doesn't change. It changes their amounts, but they both change by the same amount. They both either increase by 1 or either decrease by 1. So they must always eat the same number of sweets for 15 sunny and 15 rainy days, because we have a base case that's the same, and any change does the same thing to both of them. So they must always have the same. And that's the whole thing. Thank you for watching, and I'll see you next time.